So as discussed, we are going to revise two related topics, statistics and probability. Statistics is a shorter topic at this level because in probability we not only have the basic probability, the related theorems, but we also have random variables or probability distribution of a random variable. Okay, so in this session we will be of course revising statistics completely, and plus we will also be revising probability a bit. Just a second, there is a bit of loose connection here. Let me figure it out. Okay, fine. It's all right. Cool. Now instead of going, okay, just a second. Why is it again getting disconnected? Wait. Yeah, sorry. Huh. Now statistics also has many useful applications. Okay, if you have heard the words like machine learning, okay, there we use statistics a lot, and also some extent matrices or linear algebra, but we will not talk about that. We will only revise the basics so that we will be in a good position to solve MCQs. And of course, we will try to relate statistics with probability, especially when it comes to the distribution of probabilities. Okay, fine. Roughly, we can say that statistics deals with analysis of data sets. Right? Statistics deals with analysis of data sets. Now the data sets can be as simple as marks obtained by you in various exams, or it can also be as complicated as, let us say, uh, well, some other attributes, let's say where you stay, what your parents do, then what are your hobbies, okay, all that kind of stuff. Okay. Or maybe you can go for census. So census is a very complicated data set, right? Census is a very complicated data set because they not only ask your names, they also ask your ages, how many family members you have, where you stay, and many other relevant informations like how many languages you speak. Can you read it? Can you read that language, the script? Can you write it, or can you just speak it? Okay, fine. But we will keep our data sets to be very simple. Okay, in general, we will deal with univariate data set only. Okay, what is a univariate data set? The values that a data set has, they correspond to only one value, only one variable. Let's say, for example, height of students. Okay, height of students in a class. Okay, or let's say weight of students in the class. That is a univariate data set. You can also have bivariate, trivariate, tetravariate, pentavariate, and so on. Fine. Okay. Acha, I'll also tell you the classification of variables. Okay. So variables can be numerical, like height and weight, or they can also be categorical. So can't really quantify. Let's say, for example, do you know Hindi? Okay, that is a categorical variable. Okay, some people will say yes, some people will say no. Okay, for example, do you know Hindi? Well, you can say, I can say 0 if I don't, I'll say 1 if I do, that's fine. But essentially it is a categorical variable because it is a question whose answer is not a numerical answer, but it is a yes no answer. So in our discussion on statistics, we will keep ourselves restricted to univariate data sets, and where the values of the variable will be numerical. We'll not be discussing the categorical variables at this level. Okay, fine. So suppose we have a data set which is a univariate data set and the variable is numerical. So we have all numbers here. What do we do out of them? We can draw some conclusions based on the numbers that we have, and these conclusions are often some numbers, okay, some, let's say 5 or 6 numbers, which we believe better capture the picture of the overall data set. Okay, there are two main characteristics that we're interested in analyzing. The first one is related to the central tendency, and the second thing is related to variability. Okay, in fancier terms, we call variability as dispersion. Dispersion is essentially variability. Okay, and there are some terms that we define. For central tendency, the most commonly used quantity is arithmetic mean. We also have geometric and harmonic mean. We will see the definitions of these means later. Then we have median with a different meaning. In triangle, median means a different thing. In statistics, median means a different thing. Then we have got mode. Okay. Then in dispersion or variability, we have got a range. Then we have got mean absolute deviation. We have got quartile deviation. And we have also got the most important, standard deviation. Okay, we have got standard deviation. So what I have planned to cover today is, I will tell you the formulae. You may already be knowing them, but let's just quickly revise them. I don't think anything else they can ask from statistics, because whatever questions there have been, they have been on only the main formulae. Okay, fine. Of course, with a bit of twists. What could those twists be? We will see. Okay. First measure of central tendency is arithmetic mean. If our data set contains independent values, n values, x1, x2 up to xn, then the arithmetic mean is essentially the average, 1 upon n into summation xi as I goes from 1 to n. If we have a frequency distribution, okay, if we have a frequency distribution, it means suppose the data value x1 appears f1 times, x2 appears f2 times, and so on. Suppose xn appears fn times. Okay, then how can we modify our formula? We can just use the multiplication. Instead of adding x1 f1 times, we can just say multiply x1 by f1, multiply x2 by f2, so on, and the denominator we have to basically add all the frequencies. That will give us the total number of data points in that data set. Okay, is this clear?
Yes, sir.
Yes, sir.
Now, there is a reason why I included this formula. Okay, this formula later on will become the formula for expected value of a random variable x. Look, what I'm going to do now is, I'm going to assign each of these variables x1, x2 to xn, or each of these values a weight. Okay, what weight are we going to assign to them? We are going to assign a weight that is their associated frequency upon the total number of data values, plus f3 by n into x3, and so on up to last fn by capital N into x. Okay, now if you recall the definition of probability of an event, let's say x1 is the outcome, then can I not say that this is the probability that the random variable takes the value x1? Yes. Probability that the random variable takes the value x2? probability that the random variable takes the value x3, so on till pn x. So expected values, you may be aware of the formula. It is summation pi xi as I goes from 1 to n. So the expected value in random variables or in probability distributions is essentially the arithmetic mean of a frequency distribution. Okay, or at least we can relate the two very well because we know the definition of probability. Values favorable to some event divided by the total number of values, if you remember that. Okay, so there is a reason why I have included this formula despite you knowing it already. It's the expected value formula. Okay, fine. Any doubt here?
No, sir.
No. Okay. Okay. Now suppose we have some values and let a number capital A be subtracted. Okay, let a number capital A be subtracted from each data point. We will get a new data set, right? Di equal to xi minus capital A. It turns out that the new mean d bar is equal to the old mean x bar minus the number that you choose. Okay, or the number that you chose. Okay, this property is called shift of origin property. What is it called? Shift of origin property. Now this a need not always be subtracted. If a is negative, then we can say that if we add a number to every data point, then the mean also increases by that particular number. Okay, you can verify this. I am not going to do it for you. For homework, you can say, what if we multiply every data value by some non-zero constant c? So suppose we have cx1, cx2 up to cxn. What will be the mean? Will the mean also get multiplied by that? What do you think? Yes? You can just do it. Add and divide by n. The new mean will also be c into old mean. Right? Okay. Improve it. Now what they may do is they may transform xi to mxi plus c. Okay, a linear transformation. And they will ask you to calculate the mean. Right? I hope you understood what I added here. So here in the blue box, in this box, I have not only multiplied every data point by that c or the number, the scalar m, but I've also increased each data value after multiplication by some constant c. Okay, so what will happen to the new mean? You can answer that. Such questions can come, or rather they have come in IISER aptitude test. Okay. Then suppose we have two data sets. Okay, suppose we have two data sets representing the same quantity, of course, same variable. One has size n1 and mean x1 bar, other has size n2 and mean x2 bar. Then the combined mean or the joint mean, we say, okay, let me say combined mean is given by this formula. n1 x1 bar plus n2 x2 bar upon n1 plus n2. Again, the proof is easy. Okay, x bar is equal to n1 x1 bar plus n2 x2 bar upon n1 plus n2. Okay, next, geometric mean. So in geometric mean, we make an assumption. Okay, we make an assumption, and that assumption is that for all the data values, okay, we say that they are positive. Okay, because we usually do not find geometric mean if we have some data values negative. Let's say temperature. Okay, we don't find that. Okay, xi is positive. Suppose we have n data values. What is the geometric mean? Geometric mean is by definition nth root of the product x1 into x2. Okay, let me use the pi notation. Sigma means summation, product means pi means product. Have you seen this notation? Product notation, pi?
Yes, sir.
No,
Yes.
sir.
No? Okay. See, summation xi means x1 plus x2 up to xn. Okay. Pi xi means x1 into x2 into x3 up to xn. That is, so this is sigma notation for sum. This is pi notation for product. And later on in probabilities, we will also see intersection of events. Okay, and union of events. Okay, we can also see, we'll also see that. Acha. So coming back to geometric mean, the definition is nth root of the product x1 into x2 up to xn. In other words, we can also say that it is anti-log of 1 upon n into log of xi as I goes from 1 to n. Okay, should I explain this part or you have got it?
Sir, I didn't get it.
You didn't get it. Okay,
What is it?
fine. Look here. Suppose I take log of the geometric mean. Okay, wait, let me make some space here. Let me make some space. Okay. Okay. Look. What is the basic log anti-log notation? When I say that 2 raised to 5 is 32, I want, well, I will say that log of 32 to the base 2 is 5. Correct? But I alternately say that anti-log of how can I say it? Anti-log of 2. Okay, wait, just a second. If log of 32 to the base 2 is 5, I'll say anti-log of 2 is 32. No, sorry. Okay, I'll give you a simpler example. Are you people familiar with log tables by any chance?
Seen.
Okay, so typically we do it in this way. So we say if log of a number to some base is c, then we say anti-log of c to the base b is a. Okay, anti-log of c to the base b is a. Or in other words, if I say that log of 32 to the base 2 is 5, then anti-log of 5 to the base 2 is 32. Okay, so anti-log is as good as saying 2 raised to 5 is 32. Okay, anti-log of 5 to the base 2 is 32. Okay, now how does that apply to this? Look, let us call the geometric mean as G, and let's take the log now. Let's take the log. Now, which log am I taking? I'm taking log here. Okay, geometric mean. This side's log I am going to take. Now on the right side, apply two properties of logarithms. First property is log of a raised to n is n log a. So everywhere we will have this 1 upon n as its multiple, right? And logarithm of the product is addition of the logarithms, right? So it will be log of x1 plus log of x2 plus log of x3 plus up to log of xn. Understood till this step?
Yes, sir.
Now to get G, I'll just say antilog. But they have just written it using summation. And that's it. Okay, so antilog is nothing but the power, exponential function. Antilog 5 is 32 to the base 2 means 2 raised to 5 is 32. Clear?
Yes, sir.
Okay, fine. Third is harmonic mean. I'll first explain it through an example and then I'll explain the formula. Suppose I have three non-zero numbers, let's say 2, 3 and 7. Okay, I know their arithmetic mean. Okay, so 17. Okay, arithmetic mean will be 12.3 or 4. Okay, arithmetic mean is 4. Now what I do is, suppose I take their reciprocals. Okay, suppose I take their reciprocals and suppose I find their arithmetic mean. Okay, suppose I find arithmetic mean of the reciprocals. So it will be 1 upon 2 plus 1 upon 3 plus 1 upon 7 divided by 3. Okay, the LCM is 42. Okay, the LCM is 42. So 21 plus 14 plus 6. So that is going to be 41 upon 126. So first we took reciprocals of every data point, then we found out the arithmetic mean and then we again inverted it. Reciprocal of this arithmetic mean is the harmonic mean of original numbers. So it is 126 upon 41. Okay, so look, the blue part here is the arithmetic mean of reciprocals. The blue part here is the arithmetic mean of reciprocals, and because it itself sits in the denominator, what does it mean? It means we are again going to take the reciprocal. A reciprocal of this arithmetic mean is this, so that 1 sits in the numerator, signifying that. So what is the procedure to find harmonic mean? First you take the reciprocals of all data points, then you find their arithmetic mean, and at the end you take the reciprocal of your answer. Clear? Harmonic mean? Yeah. Fine. Okay, now we also have this inequality which is called arithmetic mean geometric mean inequality. We can prove this. Suppose we have n positive data points, or suppose we have n positive real numbers, then it can be proved that arithmetic mean is the greatest, followed by geometric mean, followed by the harmonic mean. We can prove this. Okay, and when does the equality hold? When all data points are identical, when all data points are identical, the equality holds. Okay, now this is one of the fundamental inequalities in mathematics. Okay, fine. So remember this arithmetic, not the geometric mean. Usually we are under the impression that okay, that's a product, so that has to give the greatest number. No, arithmetic mean is the greatest, followed by geometric mean, followed by the harmonic mean. Okay, now I'll also tell you a result. Okay, suppose we have two real numbers x and y. Okay, suppose we have two real numbers x and y and positive. What will be their arithmetic mean? X plus y by 2. What will be their geometric mean? Square root of xy. And if you find the harmonic mean by the definition which I told you, it will be 2xy upon x plus y. Okay. Now suppose we take AH. What are we going to get? X plus y by 2 into 2xy upon x plus y. And if I cancel these, I get xy, which is g squared. So I can say that g is also the geometric mean of A and M by A and H. Did you understand this? If we have two numbers xy which are positive, then the geometric mean happens to be of the two numbers also happens to be the geometric mean of their arithmetic mean and their harmonic mean. Okay, always also remember that. Okay, fourth is median. This measure of central tendency is median. How do we find it? Median roughly corresponds to the central value. Okay, so we have already said that all our data points will be numbers. Our variates or variables will be numerical, right? So we'll have numbers. So how do we find the median? By arranging the data points in an ascending sequence or descending, anything would do. In an ascending order, the middle value is the median. Okay, now there are two cases. So suppose we take n to be odd. So which value will be median? Median will be x6. Why x6? Because there will be 5 values towards its left and 5 values towards its right. If we arrange them in the ascending order or even descending, median will still be x6. So how do we find 6? 11 plus 1 upon 2. Now suppose n is equal to 12. Okay, suppose n is equal to 12. Now we cannot find the central value because the number of data values is odd, even. So what we then do is we take two central values, x6 plus x7 upon 2, right? So that's the median. How? Look, to the right of x7 there are 5 data values. To the left of x6 also there are 5 data values. So that is how we find the median if the number of data points is even. Okay, and for this, which data values are we going to pick? 12 by 2 and 12 by 2 plus 1. Those are the data values that we are going to pick. There are also formulae for calculating median of group data sets, but the formulae are too complicated. I don't think they will ask you anything related to that. Okay, so just remember the basics. If you want, you have NCERT textbook, you can refer that. Okay. The last measure of central tendency is called mode. Okay, it is called mode. What is the definition of mode? The most frequently occurring value. Okay, the most frequently occurring value. That is called the mode. Now, in some data sets, there can be two values having the greatest frequencies. In such cases, that distribution is called a bimodal distribution. Okay, let's say, suppose two data values have identical but greatest frequencies. Okay, then both are modes. Okay, and we call such a distribution as bimodal distribution. Okay, we call such a distribution of variable values as not binomial, bimodal distribution. If there are three, then we call it trimodal distribution. Okay, but that's not relevant. We will just keep in mind the definitions of median and mode. Okay, clear? Okay. Now let us start discussing the measures of dispersion. We completed the central tendency part. Now let us discuss the dispersion or variability. First measure of variability is called range. That is the simplest. Okay, so what are we going to do here? To find the range, what we do is we take the largest data value and from that we subtract the smallest. Okay, we take the largest data value and then we subtract from it the smallest data value. Okay, that is called range. Second, we call it mean absolute deviation. Okay, mean absolute deviation. Now, in some books, this is referred to as mean deviation. Okay, but please keep this in mind that the word absolute is necessary, absolutely necessary. Why? Because this signifies that you are required to take the modulus of the difference or the deviation xi minus a. A can be any number. Okay, a can be any number. But typically, A is either arithmetic mean or median. Now let us consider the case of these three data points that we considered. What were they? I think 2, 3, 7. Suppose 2, 3, 7 was somewhere here. We considered that. Where is it? Yeah, 2, 3, 7. Let's consider 2, 3, 7. Okay, let us consider 2, 3, 7. And we will see a result which is very basic, but nonetheless it's important because I want to emphasize the use of the word absolute. Okay, so suppose we have three data values, x1 is equal to 2, x2 equal to 3 and x3 equal to 7. Okay, and suppose I choose x bar to be my a, so that is going to be 4. Now suppose I calculate the deviations. Okay, suppose I call them deltas. So it will be x1 minus x bar, so it is negative 2. Delta 2 will be x2 minus x bar, that is negative 1. And delta 3 will be x3 minus x bar, so that will be 3. So you now realize that if we add all the deviations, we will always get 0. Always, if that is mean. Okay, because that is the definition of the arithmetic mean, and therefore we take absolute. Okay, therefore mean absolute deviation, if we want to find, then what will we do? We will first take the moduli of all the differences, all the deviations, and then we divide them by the total number of data values. So negative 2 plus negative 1 mod plus 3 mod upon 3. So that is going to be 2. Understood? Please understand that the word absolute is necessary in mean absolute deviation because it tells you to take only the magnitude part of the deviation, not the sign part. Is that clear? Because for arithmetic mean, some values will always be above the mean and some values will always be below the mean. Clear?
Yes, sir.
Yes, sir.
For for frequency distribution, you can use a similar formula. Capital N represents the total sum of frequencies. Okay. Third is called the quartile deviation. Okay. Third one is called the quartile deviation. So here what do is we divide the data set into 4 parts in ascending order or descending, doesn't matter. Okay, and then we define these quartiles Q3 and Q1 as the third and the first quarter point respectively. So the quartile deviation is defined as Q3 minus Q1 upon 2. What is Q3? Q3 is the point to whose right lie 25% of the values and to whose left lie 75% of the values. Similarly, we can define Q1 and the quartile deviation is Q3 minus Q1 divided by 2. Okay. Well, there are some other complications also. What if it is not divisible by 4? What if the remainder is 3? What if the remainder is 2? What if the remainder is 1? So on. But just remember what quartile deviation is. The word quar corresponds to dividing it into 4. Okay. The word quar corresponds to, or quart corresponds to 4 parts. Is that clear?
Yes, sir.
A similar word is percentile. A similar word is percentile. Now, when I say that my percentile is 99, it doesn't mean that I have scored 99%. It means that 99 students are behind me around. Okay? 99 out of 100 students are behind you. Okay, so the fraction is 0.99. What is the total number, what is the fraction of students that is behind you is your percentile. Okay, now quite often percentile can be deceiving. Okay, percentile can be deceiving. For example, let me give you an example. Suppose your rank is 73 out of 1000 students. Okay, suppose your rank is 73 out of 1000 students, and suppose in other case your, let's say, rank is 73 out of, let's say, 1 lakh students. Okay, now in the first case, if I calculate the percentile, it will be 1000 minus 73 upon 1000. That's 92.7. And if I calculate it here, 1 lakh minus 73 okay, so that is 99.92. Okay, now let us suppose that only 50 seats are available. Whatever exam that you wrote, only 50 seats are available. If someone tells you that I got 99.927 as my percentile, you'll say, oh nice. But will he or she get a seat? No, because there is only possibility if other students ahead of him or her cancel their seats, right? So sometimes percentile can be deceiving. It all depends on how many seats you have. Okay, and even in my videos, you may have heard me telling you that it's only the rank that matters, not the percentile. Percentile is only there to boost yourself. That okay, so many students are behind me, but in reality, what matters is how many students are in front of you. Right, how many students are in front of you, and that's the best example of why you should not take these indicators of dispersion as well as central tendency at their face value. Okay, you should always apply these in the relevant context. Only then, okay, I think the statistics I would say, serves you better. If you just say, okay, this is the formula, let me find it, that's fine. You are absolutely required to know all those details. But how are you going to interpret that? Here is one example. Okay? Alright. So that is the quartile, deviation and percentile. Now comes the last part. That is variance and standard deviation. So variance can also be defined as or described as mean squared deviation. Mean squared deviation. Now look, we generally pick the number from which we subtract for the deviation finding to be mean. So we always take A as x bar for variance. For mean absolute deviation, A could be median also. It could be any other number also. But here to define variance, we always pick that number as x bar. Okay. Now let's go to deviation part first. Okay, let us go to deviation part. Okay, this part. So it is xi minus x bar. Okay, that's the deviation part. Okay. Then let us consider the squaring. So every deviation is found out and it is squared. And then we take the mean of that. Okay, so we take the summation. And then we divide it by the total number of values. Okay, that is the variance. Hence we call it mean squared deviation. The purpose of mean should be now clear. Okay, we take the squared deviations, we sum them all, and then we divide the sum by the total number of data points. Is it clear?
Yes.
Variance? Yes, okay. And the positive root of variance is called standard deviation. Positive square root of variance is called standard deviation. Using the properties of summation notation, you can prove that variance is also summation xi squared upon n, or mean of the squares, not square deviation, mean of the squares minus square of the mean. Okay, so variance is also mean of the squares minus square of the mean. And because you now know that expected value is mean, we can say that variance of a random variable x is actually expected value of x squared minus square of the expected value. This formula will come later, but nonetheless it's related to the variance formula for data points. Okay. Lastly, let us discuss the shift of origin and scaling effect on variance. Okay, on variance. Suppose we have some data points x1, x2 up to xn, and let us say we shift the origin, equivalent to saying we subtract a single number from all data points. Standard deviation and variance are unaffected. Okay, standard deviation and variance are unaffected. You can prove this. Okay, in other words, we say that variance is conserved. In fancier terms, how will I say? Variance is conserved under shift of origin. Okay, that's the other way of saying it doesn't change, it remains constant. Okay, or it is invariant, we can say. But what about scaling? Is it prone to scaling? Yes. Suppose we scale xi minus a by h, then the variance is, well, it actually reduces. Okay, so sigma x is actually mod h times sigma t, or sigma d, the new variance, a new standard deviation. Okay, standard deviation new is equal to standard deviation old upon the number that you used for scaling. Okay, take the mod of that. Is that clear?
Yes.
Yes, sir.
Okay, now see, this is also justified because if h is greater than 1 or less than -1, okay, in some sense I can say that on dividing your data points by a number greater than 1, you're kind of downsizing them, correct? If let's say h is 2, you're halving everything. So accordingly the mean will also get halved. So if you now decide to consider the deviations, square them, add them and take the mean, the value is bound to be smaller than the original variance value, and that is something that is reflected in this formula. Okay, that is reflected in this particular formula, that the new standard deviation is the old standard deviation upon absolute value of the number that you chose to scale the data points by. Correct? Understood? Okay, fine. Coefficient of variation. Huh. Okay, sometimes the question can come like, which of the two data sets, is more variable? Which of the two data sets or possesses more variability? So for this, to answer this question, see, I can also use range to compare the variability, but range may not be a very good indicator. Okay, let's say for example, let's say I have a batsman, okay, who got out on his very first ball, so did not score any runs, and let's say in all of his other innings, he was in between 28 in his 20s and 30s. Okay, but suppose he scored a century in one of the matches. So here the range will be 100. Now you know that except for the last two values, there isn't much variability there. Okay, but if I consider something like 5, 9, or let's say 5, 17, 27, 49, 71, and let's say 89. So here the range is what? 89 minus 5. So that is 84. So the range is smaller, but you see clearly there is more variability here. Because of the last two values here, it is more, the range is greater in the first data sets. Okay, for the first data set. So what we do is, we define coefficient of variation as ratio of standard deviation to mean. Okay, ratio of standard deviation to mean. If we want to express it as a percentage, then we multiply it by 100, and the data set having larger coefficient of variation is said to have more variability. Okay, which of the two data sets is more variable? Answer is the one having greater coefficient of variation. Okay, you can try this as homework. Question is, find the coefficient of variation for two data sets here. Will you be able to do that? Of course you can, right? So simple question. Okay? And tell me which one of them is variable. What is our intuition telling us? Intuition is telling us that if this is data set D1 and this is data set D2, then the coefficient of variation for D2 is greater than coefficient of variation of D1. That is what we are expecting. Okay, you can try that and tell me tomorrow whether you indeed got that answer. Understood? Okay. Last is the standard deviation of joint data set. Not recommended to memorize the formula, but if in case they ask you, then you should know it. Okay. So let me tell you the meanings of every term here, each and every time. Sigma squared is the variance of the joint data set. sigma 1 squared and sigma 2 squared are variances of individual data sets. Okay, variances of individual data sets. N1 and N2 are their sizes. And the numbers D1 and D2 are the differences between the arithmetic means of the individual data sets, and X bar is the arithmetic mean of the main data set, whose formula we saw earlier. Okay, so X1 bar, X2 bar are individual means, and X bar is the joint mean. And D is the difference between X. It doesn't matter now which one of them is greater, because it has to be the square, right? D1 squared. So you can prove it that sigma squared is N1 sigma 1 squared plus D1 squared plus N2 sigma 2 squared plus D2 squared upon N this. N2, if you have not seen the formula, don't get too frightened. It's very less likely that such a question will come in the exam, because it is only formula based. It is not testing you. It is not testing your understanding of that particular concepts. Okay, that scaling part and the change in variance, that part can come. Okay, this part, sigma D, the new variance is old variance upon absolute value, but I'm not betting too much on this part. ठीक है, standard deviation of joint data set. ठीक है, okay. Alright, that's what I wanted to take from statistics theory. If you feel any part is missed, let me know, I will cover it. How many of you had studied statistics in 11th standard? Okay. Okay. You all of you, okay, nice. And how much of that do you remember? That is also a concern.
It was mostly basic. Well,
You said you did not have geometric mean and harmonic mean, right?
geometric mean there was, harmonic mean was.
Okay, but now it's not. Okay, great. Let's now go to probability. All right. Now, as you might be knowing that basic probability terminology is developed in 11th standard, and it is applied to probability distributions in 12th standard. I guess for CBSE or NCRT, you even have Bayes theorem and all that stuff in 12th, right?
Yes, sir.
In this state board, in Maharashtra state board, there is a clear distinction between probability and probability distribution, in the sense that everything till Bayes theorem is covered in 11th standard in probability itself. So we begin by random experiment, and the probability ends with Bayes theorem, and then in 12th standard directly we start with probability distributions. Okay, so when I was in the 12th standard, we had 3 probability distributions: binomial, Poisson, and normal distribution. Now Poisson and normal have been dropped, and only binomial distribution is remaining. That's a good news. Okay, it's a good news. Anyways, we are going to revise the whole of probability together, depending on the time. Of course, we'll require one more lecture to cover the whole of it. Okay, the whole of probability. Acha, we may require this formula definitely in binomial distribution. NCR is n factorial upon r factorial into n minus r factorial, with one inclusion that 0 factorial is equal to 1. Okay. Alright, so with that formula, let's jump into the terminology of probability. And with the good news is we know we know things from set theory. We have covered that. Okay, because our approach towards probability is going to be a set theoretic approach, because right from sample space and event, all of them are sets. Okay, then when we say mutually exclusive events, we mean that the events represent disjoint sets. When we say collectively exhaustive events, we mean that union is the sample space. Okay, all that stuff. Anyways, let's start. Basic four terms or three terms: random experiment, sample space, sample size, and event. Okay, what is a random experiment? Two things are important in the definition of random experiment. Okay, what is a random experiment? An activity where the outcome cannot be predicted. The outcome cannot be predicted prior to the trial with 100% certainty. These words are important, because we'll say, if I toss a coin, I know it's either a head or a tail. If I say head, I have predicted, I may be right, I may be wrong. Unless we do it, we will never come to know. Okay, so an activity where the outcome cannot be predicted prior to the trial with 100% certainty, but, second point is important. The set of all possible outcomes is known. In other words, we know from what set the outcome is going to be, but we cannot predict it unless we do the experiment. Such experiment is called, or such an activity is called random experiment. Typical examples are tossing a coin and rolling a die. We can increase the complications by considering one coin and one die together, or two coins, three coins. That's all in binomial distribution. Okay? All right. That is random experiment. Number two, sample space. What is sample space? Sample space is nothing but the set of all possible outcomes. Okay, sample space is the set of all possible outcomes of a sample space. Okay, of a random experiment, sorry, of a random experiment. Of a random experiment. The standard symbol for sample space is S. Okay, what is sample size? Number of elements in the sample space. We will usually consider finite sample spaces only. Okay, and what is an event? Important. What is an event? Any subset of sample space. Is called an event. Okay, any subset of sample space is called an event. Is it clear?
Yes, sir.
Yes, sir.
Yep, okay, that's important. Any subset. Okay, so if sample size is, let's say M, then total number of events is going to be 2 raised to m, defined on that sample space. Okay, it's 2 raised to m. We have seen this, right? We have seen this, that the number of subsets of any set is equal to 2 raised to the number of elements in the number of elements that set has. Okay, fine. So if you understand these 3 or 4 terms well, random experiment, sample space and event, then the rest of the terminologies of probability, and they are not difficult to understand. Okay. Let's go to mutually exclusive events. What is the definition of mutually exclusive events? Now you know events are sets. Okay, so even let us say it belongs to the sample space and E2 should also belong to the same sample space. But suppose even intersection E2 is a null set, then those events are called mutually exclusive events. Okay, so occurrence of one of those events prohibits the possibility of the occurrence of the other. Okay, so any event and its complement, any event and its complement, they will always be mutually exclusive. Is it clear?
Yes.
See,
Yes, sir.
students often remember this part, that their intersection should be a null set, but they tend to forget that the events should be defined on the same sample space. Otherwise, the events will always be distant. Okay. Then we have collectively exhaustive events. Now, what are collectively exhaustive events? 2 or more events are collectively exhaustive if their union is sample space. Okay, their union is sample spaces. See, look, by definition, exhaustive events and mutually exclusive events, they mean something else. Okay, let us now try to come up with 4 cases where the events are mutually exclusive but not collectively exhaustive, not mutually exclusive but collectively exhaustive, both of them and neither of them. Okay, so let us consider the sample space 1, 2, 3, 4, 5, 6, rolling a die. Okay, rolling a die. Now look, let's say mutually exclusive, collectively exhaustive. Okay, let's consider 4 possibilities. Okay, now suppose we want both of them. We want them to be mutually exclusive, but we also want them to be collectively exhaustive. So suppose I call E1 as 1, 2, 3 and E2 as 4, 5 and 6. Are they mutually exclusive? Yes, because their intersection is a null set. Are they collectively exhaustive? Yes. Now these you will see, these are complements of each other, if you see. Okay. Now suppose we want 2 events defined on the sample spaces which are mutually exclusive but not collectively exhaustive. Okay, so suppose I keep E1 and suppose I take E2 as 4, 5. They are mutually exclusive because they do not have any element in common, but they are not collectively exhaustive because their union is not giving us the sample space. Okay. Now suppose we want collectively exhaustive events but we do not want mutually exclusive events. So let's keep E1. And suppose I keep, okay, it's not, let me call it as E3. And suppose I take E4 as 1, 4, 5, 6. Now are they mutually exclusive? No, because both E1 and E4 have one element common, that's one. Okay. Are they collectively exhaustive? Yes. Okay. Now suppose we want neither of them. Okay, we want neither of them. So let's keep E1 and let's keep E5 as 3, 4. Okay, these 2 events are neither mutually exclusive because they have 3 common, They're not collectively exhaustive because their union is 1, 2, 3, 4, which excludes the other two elements in the sample space. Is that clear?
Yes, sir.
Great. Okay. Now let us go to the classical definition of probability. Now, in the actual definition, we also make some assumptions, but for our problem solving, this should be clear. Okay, in the classical definition of probability, we say that let each outcome, okay, let each outcome of sample space be equally likely. Let each outcome of sample space be equally likely, and suppose there are capital N total outcomes. Okay, capital N total outcomes. And then the probability of an event A, and suppose number of elements in an event A is n, A an event defined on such a sample space. Then its probability Na is equal to capital N with small n upon capital N. And by this very definition, the probability can never exceed 1 and it can also never be less than 0. When A is sample space, it is a certain event, and when A is a null set, it is an impossible event. Okay, fine. Now look here. When we consider S as 1, 2, 3, 4, 5, 6, and if I say that the die is fair, then I can say that each probability is 1 upon 6. Or let's say probability of 3. But if I do not know that the die is fair, and it's very difficult to decide whether it is fair or not, right? In that case, I cannot say that probability of 3 is 1 upon 6 because we do not know that all outcomes are equally likely or not. So in that case, how do we define probability? In that case, we define the probability by using limits. Okay, we define probability using limits. Okay, so what we say is this. Modern definition. Okay, so in the modern definition, we say let the trial be run n times. Okay, let the trial be run n times, and let n trials favor an event A. Then the probability of the event A is defined as the limit of n upon capital N as n tends to infinity. Okay, I hope you understood what we discussed just now. But to keep on doing the experiment, if the die is fair, in this case n upon capital N, all of them for 1, for 2, for 3, for 4, for 5 and for 6, each one of them will converge to 1 upon 6. Okay, each one of them will converge to 1 upon 6. Clear? Is it understood or shall I explain it again?
Clear, sir.
Clear? Okay, Aishwarya understood?
Yes, sir.
Okay, very good. Alright, now let us consider the union and intersection probabilities. Okay, so we will consider that A and B are two events defined on the same sample space. On same sample space. Okay. Yeah. Now you very well know what A union B means. The event A union B means at least one of the two events. Okay, let's say, yeah, either A occurs or B occurs or both occur. Okay, and what is the formula for probability of A union B? Probability of A plus probability of B minus probability of A intersection P. Okay, in other words, probability of A union B is number of elements in A union P upon number of elements in the sample spaces. Now what does A intersection B represent? Both occur. And what is the probability of A intersection B? Number of elements in A intersection B upon number of elements in the sample spaces. Okay, so union means at least one event occurs, and intersection means both occur. Okay, that's intersection probability and union probability. In particular, we are going to make use of this probability of A union B in conditional probability and multiplication theorem, and for the theorem of total probability, we were going to make use of the union probability. Okay, let me write it down. Union is required in the theorem of total probability. And intersection is required in conditional probability. Now, essentially, we have reduced our study of probability to set theory, right? So every operation of sets on sets is going to have some meaning in the terminology of probability. Okay, intersection refers to then conditional probability, or we'll at least use it in conditional probability. Okay, all right. Complement of an event, we know that probability of a complement is 1 minus probability of A. Now there is a specialty for events A and its complement. They are mutually exclusive because their intersection is null set, but they are also collectively exhaustive. We say that any event and its complement partition the sample space. Now partitioning is an important operation because via partitioning we always get events which are mutually exclusive as well as collectively exhaustive. Okay, so we can have two or multiple such partitions over the same sample space. Okay. Acha. Now there is one more term that we use: odds in favor and odds against an event. Okay. Acha. So let us suppose that X represents the number of elements in an event and suppose Y represents the number of elements in its complement. Okay, so how do we define odds in favor of A? X upon Y, and odds against an event is y upon x. Note that probability of A is x upon x plus y, and probability of A complement is y upon x plus y. It is to be noted here that odds can be greater than 1. Okay, can be greater than 1, but probabilities can never be. Do you understand this?
Yes, sir.
Okay, fine. So, fine, I think I'll stop here. We will continue with the probability discussion tomorrow, and tomorrow will also cover random variables. Okay, fine. Because conditional probability and independent events will take some time, maybe 10 minutes. So I will stop here. We will continue with this tomorrow. But tomorrow, no matter what, we're going to complete the theory of probability. Okay, clear?
Okay, sir.
Okay, complete the homework. Yes.
Sir, can you give an example for that odds in favor and odds? I didn't understand like why are we using x5y?
Okay, I don't know whether you follow this, but there is a sport in which they race the horses. Okay, and if in the newspaper, if you read that particular column, there they say odds in favor of one particular horse winning a race. So their language is not in terms of strict probabilities, but odds in favor and odds against an event. Okay, look, for example, suppose my sample space is 1, 2, 3, 4, 5, 6. Okay, and suppose my event A is 1, 2, 3, 4. Okay, so x is 4 and y will be 2. Got it? So for my event, odds in favor of A will be 4 by 2, so 2. Why 4 in the numerator? Because x is 4. Why 2 in the denominator? Because in its complement event there are 2. Okay, we generally keep it as 2:1. We don't say 2. Okay, just say 2:1, but we can also write it as 2. Just another way of representing probability of an event, combining its complement also. Okay?
Okay, sir.
Yeah. Fine, so we'll stop. Okay, great. So we are revising probability. We have already completed revision of statistics yesterday, and some topics from probability we have revised. And well, I want to highlight 1 or 2 results from statistics which I told you are applicable in probability, in particular random variables. The first result is the mean of the distribution. Okay, so it is summation fi xi upon summation fi. Okay, so if I call the summation fi as capital N, and if I write it as summation fi by n into xi, that essentially becomes summation pi xi, where p represents the probability that the random variable is going to take the value xi. Okay, so expected value or expectation of x is essentially that. Okay, second thing is variance of x. Okay, how did we define the variance there? It was summation of fi into xi squared upon capital N minus x bar squared. And we actually use the same formula for finding variance of a random variable. Okay, what is the formula? Expected value of x squared means mean of x squared minus square of the expected value. Note these two formulae, we will see them today in a different form. Okay, all right. The other thing that we noted is our study of probability has its basis as set theory. So our discussions on random experiment and sample space and events, okay, tell us the same thing. What is this? What is a sample space? Sample space is a set, and events are subsets of sample space. Okay, events are subsets of the sample space. Then mutually exclusive events represent disjoint sets. Okay, mutually exclusive events represent disjoint sets, and collectively exhaustive events represent union of the events. Okay, union of the events which gives us the original sample space. Okay, yesterday we had the sample space of all possible outcomes when a single die is rolled, and we considered 4 possibilities. 2 events which were not mutually exclusive, not collectively exhaustive. They were both exclusive and exhaustive, and one yes, the other no. If you remember, we have made a list of all 4 possibilities, right? Okay, just to emphasize that collectively exhaustive doesn't necessarily mean mutually exclusive, and vice versa. Okay, then we listed down the classical definition of probability and also the modern definition of probability. In classical definition, the probability of an event refers to the ratio of the list of all possible outcomes which favor that event upon the size of the sample space. Okay, this is the number of elements in the sample in the event. Okay, probability is never greater than 1, never less than 0, and also the events whose probabilities are 1 and 0 don't tell us much about anything, right? Sample space is something which always takes place, so its probability is 1, and impossible event has its probability 0. Okay, fine. And what is the modern definition? In the modern definition, we say let the experiment be repeated n times. Okay, let the experiment be repeated n times, and suppose out of those n outcomes, n small n outcomes favor or are in favor of a particular event, then this becomes the definition of probability of event. Okay, for us at this level, both the definitions we can say they are same. They are not going to make any difference if we apply the classical or the modern definition of probability. Okay, fine. Then what are union and intersection probabilities? We know this. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. Union means at least one event happens. Okay, and what does intersection mean? Both must happen. Right, both must happen. Complement of an event, yeah. See, any event and its complement automatically form mutually exclusive events and collectively exhaustive events, right? We also say that when there is a case like that, it actually partitions the original sample space. Okay, it actually partitions the sample space into 2 disjoint sets. Okay, we will see partition even today for in multiplication theorem and in Bayes theorem. That's complement. Odds in favor, odds against an event, we won't discuss that. Okay, so our discussion today will begin with conditional probability and independent events. Okay, conditional probability and independent events. And to put my point, let us again consider the experiment of rolling one die. Okay, suppose I consider the random experiment of rolling one die. Can you tell me the sample space? 1, 2, 3, 4, 5 and 6. Okay, and we are assuming that the die is fair. Now consider the event A given by 1, 2, 3. Okay, consider the event A given by 1, 2, 3. consider the event B given by 1, 2, 4, 5 and consider the event C given by 1, 2, 3, 4. Can you tell me the individual probabilities here? What is probability of A? 3 by 6 or 1 by 2? What is probability of B? 4 by 6 or 2 by 3? What is probability of C? Again 2 by 3. Is that clear? Simple, right? So B is as likely to happen as C because they have same probabilities. A is less likely to happen because A has a smaller probability. Okay? Now, I define the conditional probability as follows. Okay, this means probability of occurrence of A. What does it mean? Probability of occurrence of A under the condition that B has happened. Now let me tell you one thing here. The random see, when I say that B has happened, the random experiment has already been conducted, the outcome has been noted, and it has been found that the outcome belongs to B. Okay, that's the thing that is known. What is the probability that the outcome also belongs to A? That is what we want to find. So we are not repeating the random experiment again. That we are doing the experiment only once and it has found that B has happened. Okay, in the same event or for the same outcome, what is the probability that it also belongs to A so that we can say that A has happened? Okay, to understand this, let us first build the Venn diagram. Okay, often Venn diagram helps us visualize things better, right? So suppose this is a sample space S and suppose this is A and suppose this is B. I'm showing them in their most general cases. Okay, so some part will be common. Now, when I say under the condition that B has happened, what I mean is my sample space is no longer the original sample space, but my sample space is this much only. Okay, now how much of it belongs to A? The intersection part, right? So I can say that this is NA intersection B upon NB. If we divide the numerator and denominator by the sample size, I will get the probabilities. Probability of A intersection B upon probability of B. Is it clear?
Yes, sir.
Okay. Now, if probability of A given B is equal to probability of A, then A and B are said to be independent. Okay. And if probability of A given B is not equal to probability of A, both possibilities exist, either it will be greater or lesser, okay, then A and B are said to be dependent. Now let us find out probability of A given B in our case. Okay, probability of A intersection, okay, we already have the answer. Okay, let's use the definition. Okay, what is NA intersection B? Okay, how many elements are there in A which are also there in B? 1 and 2. So NA intersection B is 2. Okay, and how much is NB? How many elements does B have? 4. 1, 2, 4 and 5. So this is half. But what is the probability of A? That is also half. So A and B are independent. Okay, A and B are independent. Now this result is symmetric. It means P of B given A has to be equal to P of B. Whenever P of A given B is equal to P of B, P of A. Now let's find it out. Okay, what is probability of B given A? Anyone? Let's apply the formula first. Let us apply the formula. N B intersection A, that is the intersection B actually. Complement is a commutative operation upon Na. Okay. Now how many elements are there in B intersection A? Can anyone tell me? Still two. Still two. How many elements does A have? 3. 1, 2, 3. Right? A has 3 elements in it. And what is probability of B that we had noted earlier? Was it 2 by 3? Yes, it's 2 by 3. So again we got the same. So whenever P of A given B is equal to PA, P of B given A automatically becomes equal to P of B. Is that clear?
Yes, sir.
So it can never be a case that A depends on B, but B is independent of A. No. If they are dependent, they both will depend on each other. If they are independent, if one is independent of the other one will also be independent of the first. Okay, fine. Now let us check for C. Okay, let us check for C. Okay, now how many elements does A and C have in common? 2, right? Oh, sorry, not 2, 3. 3 are common. And how many elements are there in C? 4 elements. Now see, this is actually greater than probability of A, because probability of A is 50%, half. This is 75%. So we draw the conclusion that occurrence of C improves, or let's say favors, occurrence of A. Had it been less, we would have said that occurrence of C does not favor occurrence of A. It doesn't mean exclusion, total exclusion, no. It just means that the conditional probability becomes smaller than that. Let's try the other way. Let's try probability of C given A. Okay, so the numerator will again be 3. Now how many elements does A have? 3. That's one. Now occurrence of A means C has already occurred, because every element in A belongs to C. Right, so C given A is 1. So occurrence of A makes occurrence of C certain. Got it?
Yes, sir.
Yes, sir.
Okay, fine. So that is conditional probability and independent events. Now let us go to multiplication theorem, or theorem of total probability. Okay, first let me cover the multiplication theorem in its simplest form. Multiplication theorem in its simplest form. So in multiplication theorem, what we do is we still write the definition of conditional probability, but we write it in this way. Probability of A given B into probability of B is probability of A intersection B. Alternately, we can also write it as probability of B given A into probability of A is probability of A intersection B. ठीक है? Clear? This part, multiplication theorem. We call it multiplication theorem because we involve product of probabilities. Hence we call it multiplication theorem. Followed? Similarly, look, we can also write addition theorem, where we add or subtract the probabilities. It automatically becomes the addition theorem. Okay, what is the addition theorem? The same. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. Now, depending on the available information, we can either use PA given B into PB or PB given A into PA here. Okay, and just combine the multiplication theorem and addition theorem together depending on our requirement. Is that clear? Addition theorem and multiplication theorem?
Yes, sir.
Okay. Great. Let's now go to the theorem of total probability. Let us now go to the theorem of total probability. So what is given? What is given here? Given is some partition of sample spaces into n subsets. Say E1, E2 up to En. Now look, by definition, partition refers to what? Mutually exclusive events. Okay, mutually exclusive events and collectively exhaustive events. Both. Usually that's not the case, but the moment we say partitioning, both things automatically come into picture. Is it clear?
Yes, sir.
Yes.
Okay. Now what does total probability theorem say? Let A be any subset of S. Can I say that NA is equal to N A intersection E1 plus N A intersection E2 plus up to N A intersection En? Yes, I can say that. And if I divide both sides by the sample size, I can say that probability of A is summation of probabilities of A intersection Ej as j goes from 1 to n. Is this part clear?
Yes, sir.
Now let us go to multiplication theorem and bring it here. Let us go to multiplication theorem and bring it there. Let's go to multiplication theorem and bring it here. Okay, so what can I write here? A intersection Ej means probability of A given Ej, okay, into probability of Ej. See, look, because having already stated that the partitions are A1, A2 and En, well, E1, E2 up to En, the probabilities of these events are already known to us because we have partitioned the set accordingly. Okay, so it makes more sense to write A given Ej into P of Ej. Is it clear?
Yes, sir.
By mistake, if you write the other, then you will get PA equal to PA, nothing else. Look, suppose you write it as P of Ej given A into probability of A. This is going to cancel this, and you know now because well, like Ej given A, that means that particular partition will take place. Okay, so all those probabilities will add up to 1 because Ej's are all mutually exclusive events and collectively exhaustive events. Is it clear? we can write it. P B given A into P is also there, but we prefer to write it here because write the other way because partitioning already uh, facilitates the corresponding probabilities. Okay, is it clear?
Yes, sir.
Okay, fine. Okay, now let's go to Bayes theorem. What is Bayes theorem? See, the theorem of total probability says that the partitioning is already taken place and we are finding the probability of an event A. We're essentially expressing it using addition theorem or well as addition of probabilities of the intersection probabilities. Okay, so here we use A given EJ, but in specifically for Bayes theorem we do the opposite. So we find probability of EI given A. Okay, we find the probability of EI given A. Now look here. Again, everything that we wrote for given of total probability, basically we write the same thing here also. Okay, even for Bayes theorem we write the same thing. Given some partition of S into n subsets, so on, and let A be any event. Okay, let A be any event. Now we ask for the following probability. Suppose A has already occurred. What is the condition? What is the condition probability that E1 has also occurred or EI has also occurred? Look, usually we will say EI intersection A upon what probability of A? Okay, this is from biconditional probability, right? Biconditional probability. Now to find PA we use multiplication theorem. To find PA we use the multiplication theorem which we saw here. Okay, we use multiplication theorem to find PA. Okay, now what about P of EI intersection A? Okay, to find PI intersection A, again use multiplication theorem. So total probability for the denominator and multiplication theorem for numerator. Look, let's borrow the statement of multiplication theorem. This is the statement, correct? This is the statement of multiplication theorem. Now what am I going to do? Oh, sorry, not this one. This one. Look, let B be replaced by EI. Let P be replaced by EI. Okay, so the PEI given A into PA part that has already been used. So now we use the other part. Okay, so for P of EI intersection A, we say in the numerator, what will I write? P of EI into P of A given EI. Okay, that's the numerator. EI into A given EI probability. And the denominator, of course, we find out the conditional probability or total probability. That's P. Okay, is that clear?
Yes, sir.
The theorem is understood better if we solve problems, which we will do once we cover all the theory. Okay, so there are 4 important theorems. First is addition theorem, which gives us the union probability. Then we have got multiplication theorem, which gives us the conditional probability. Third, we have got my theorem of total probability. Again, we have a partition. And then finally we have got Bayes theorem. Now for Bayes theorem, we use some terminology which is given in NCERT. The events into which we partition the sets, the sample space set, those events are called hypotheses. Okay, and the probabilities of the events EI, they are called priori probability of the hypothesis here, or priori probabilities. Prior means before. Okay, and P of EI given A, which we aim to find, they are called the posteriori probabilities. Prior means before the occurrence of A, well, or without having any information about whether A has occurred or not. And P of EI given A stands for posterior probability, meaning what is the probability of a respective event if the event A has already taken place. That is called posteriori probability. Is it clear?
So,
Now I'll also tell you a rule of thumb. See, sometimes what happens, you recognize that this problem is on Bayes theorem. Okay, you recognize that this problem is on Bayes theorem, but you are confused about the way we should partition it. Especially, see, this is going to happen when we have B and B complement and A and A complement. Okay, so look, suppose this is the sample space. Okay, suppose this is a sample space. The one above represents B. Okay, the one above represents P and the one below represents B complement. Suppose. Okay, so this is B and this is B complement. And suppose if I draw something like that, suppose this represents A. Suppose this represents A, then automatically this will represent A complement here. Okay, now you have to remember the statement of Bayes theorem. It is EI given A. That is what they always ask us to find. EI given A. Now what does that mean? Whatever event that you write here, okay, whatever conditional probability they have asked, you have to select this as one of the partitions of the set. Did you get what I'm saying? See, suppose there are two events given A and B, and of course we can also find their complements. So there are two ways in which we can partition the sample space. Either we can partition our sample space as B complement, or we can partition our set as A complement. Now, in which way we should select the partition? That is decided by the statement of the Bayes theorem. EI given A is what the Bayes theorem gives us. EI given. What does it mean? It means, look, suppose they ask us to find the probability of B given A, then what partitioning should we select? B complement partitioning should be selected. And if they ask us to find probability of A given B, then which partitioning are we going to select? A complement partitioning is to be selected. Understood?
Yes, sir.
Have you people solved the problems on Bayes theorem in theory?
Yes, sir. I've solved NCERT level 1.
Yeah, that's enough. That's more than enough. Others? Okay, then please remember the rule of thumb. Okay? Fine. So that completes the theory of probability. Now let us go to random variables. Okay, wait. if you want, we can solve a problem on Bayes' theorem from NCERT. Fine? We can solve a problem on Bayes' theorem. Yes.
So I have a doubt on a question.
On probability?
Yeah, I was just looking around since you asked.
Yeah, sure. What is that?
Will remember the page number.
On NCERT itself.
Yeah.
Probability. Okay, okay. I think Bayes' theorem is the second last exercise. Last one is binomial. Oh, no, 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 no. Previous is probability mass functions. Okay. Okay, yeah, I think this is Bayes' theorem. Yes, 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 this is Bayes' theorem. Okay, let's take this blood cell problem, a blood test problem. Okay, let's take this blood sample problem. Okay, fine. Let's read the problem. Let's try to identify the sample space and the partitioning events and the other events also. A laboratory blood test is 99% effective in detecting a certain disease when it is in fact present. However, the test also yields a false positive result for 0.5% of the healthy person tested. That is, if a healthy person is tested, then with probability 0.005, the test will imply that he has the disease, also called false positives. Okay, if 0.1% of the population actually has the disease, what is the probability that a person has the disease given that his test result is positive? Okay, now look here. There are two ways in which we can partition the sector. Okay, the sample space. Test positive, test negative. And the other way in which we can partition the same sample space would be okay, people having disease. Okay, let's say disease yes, and disease no. Is that clear?
Yes, sir.
Yes, sir.
Okay, okay. Now let us go for the probability that they want us to find. Okay, they want us to find the probability that a person has the disease. Okay, probability that the person has the disease given that his test result is positive. Now, if we correctly recognize this, then half of the job is done for us. Why? Because if you recall the theorem of Bayes, a Bayes theorem if you recall, then you know that event A in the Bayes theorem notation is a person tests positive. Correct? And event E1 refers to the person has the disease. Did you get this part? So event E2 obviously would mean that the person doesn't have the disease. Everybody, did you get this part?
Yes, sir.
How we identified the partition. It could have also been the person tests positive, doesn't test positive, assuming that everybody does the test. Okay. See, this EI given a part is important. Okay, EI given a part, that is actually important. Okay, fine. Now, having correctly recognized the events, is it possible? Is it possible to find out probability of E1? It will always be known. Is it possible to find probability of E2? Of course, because it will be complement of this. Now look, if 0.1% of the population actually has the disease, 0.1% of the population actually has the disease, it means even person has disease. 0.1% means 0.001. And what will be probability of it? It will be complement of even, right? 0.999. Have you understood this?
So,
Yes.
Okay, okay. Now, are there any other numbers to be interpreted? 99% effective in detecting a certain disease when it is in fact present. Now, what does that 99% probability mean? Or 99% effectiveness means? It means probability that, okay, see, okay, let's read it again. In detecting a certain disease when it is actually in fact present, when it is present. So, given that person has a disease, the probability that the test is positive is 99%. Have you understood this?
yes, sir.
However, the test also yields a false positive result for 0.5% of the healthy persons tested. That means if a healthy person is tested, then with probability 0.005, the test will imply that he has the disease. What does it mean? It means probability that, okay, probability that the person tests positive, given that he doesn't suffer from the disease. What is that probability? A given E2. Healthy person, so that is E2. Healthy person is E2. A is person test positive. What is that probability? 0.005. Right? 0.005. Let me use blue color here. Let me use blue color here. Okay? That's 0.005. Okay, now we can apply Bayes' theorem effectively. Okay, now we can apply the Bayes' theorem effectively. What does it mean? We want to determine probability of E1 given A. Okay, E1 given, that means the person, what is the probability that, okay, given that the person has tested positive, what's the probability that he actually suffers, right? E1 given A, given that is tested positive. Okay, first it's A, E1 intersection A upon probability of A. Okay, probability of A. Now, how can we find the probability of A using the theorem of total probability? Does anyone remember that? It's probability of A given E1 into probability of E1 plus probability of A given E2 into probability of E2. That's the theorem of total probability. Where is it? See, PEJ into PA given EJ. That's the same thing. Okay, next, what should I write in the numerator? Probability of E1 intersection A. That will be probability of A given E1 into probability of E. Is that clear?
Yes, sir.
Yes.
Okay, A given EI into probability of EI. Let's substitute the values now. Let us substitute the values. Okay, E1 is 0.001, E2 is 0.999, E1 is 0.07. A given E1 0.99, A given E2 0.005. Okay, so it will be Okay, first of all, for 99, let's shift by 2. Let us shift this by 1. Okay, by 3. So 99 into 1 plus 0.5 into 999. So it will be 99 upon 99 plus 999 by 2. Okay. Okay, so 99 into 2 upon 99 into 2 plus 999. And divide by 9 now. 11 into 2 upon 11 into 2 plus 111. So it will be 22 upon 133. Have you understood this?
Yes, sir.
Okay. Let us see if our answer is correct. What exercise is that? 13.3, question number 5. Question number 5, 22 by 133. We have got the same answer, 22 by 133. Understood?
Yes, sir.
Exactly. So, based on what conditional probability you want to find, the first event there, that is how you should choose your partitioning. Okay, that's it. Once you remember that rule of thumb for Bayes theorem, then the rest becomes easy. Okay, especially in the exam, if you have your strategy ready, then you can easily solve the problem. In some problems, we can also assume the total number of persons suffering, let's say, to be total persons, and then everything else you can partition and just get the number. Okay, have you ever seen my video where I take the sample size to be a particular number, and then I just find the all four things, like how many things are here, 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 and accordingly I can find the probabilities. You can also do that. Okay, did you get what I said or no?
I got it. You can use for one.
Which one, using Bayes theorem or using the thing that I talked about?
721. Probably based here.
One more example on Bayes theorem.
No. It was on the example 21 on NCRT.
Oh, okay, your doubt. Okay. Example 21. Which exercise?
Before exercise 31.
Okay. Example 21. This one, right? Okay. Example 21.
So can you do this using that thing that you just spoke about?
Okay, fine. We'll first do it using Bayes theorem, and then I'll bring my trick into play. Okay.
Okay, sir.
Example 21. A man is known to speak truth 3 out of 4 times. He throws a die and reports that it is a 6. Find the probability that it is actually a 6. Which probability do we want? We want the probability of actual 6. Okay, probability of actual 6 under the condition that he reports it to be 6. Okay, probability of actual 6 given the condition that he reports it to be 6. Is that clear?
Sir,
Okay. Now look here. This is going to be our way to partition the set or the sample space. So actual 6, let us call it E1. Okay. So what will be probability of E1? 1 upon 6. Correct? Probability of E1 1 upon 6. Then what will be the complementary probability? E2 5 by 6. Okay. Acha. Now they are saying he throws a die and reports that it is a 6. Find the probability that it is actually 6. Okay. Probability that, oh, okay, wait. He reports it to be 6. Okay. He reports it to be 6. Okay, so that is our event A. We still don't know that. Okay. Fine, let's see what the Bayes theorem gives us. Probability of E1 given A is in the denominator probability of A, and in the numerator it is going to be probability of A given E1 into probability of E1, right? Okay, so is that part clear? That's Bayes theorem. Okay. Now, let us write down using the theorem of total probability of A. What will it be? That's what we want. Okay, it's not given explicitly. P of A given E1 into probability of E1 plus probability of A given E2 into probability of E2. Okay. Now, out of these, how many probabilities do we know? We know 2 of them. E1 is known, 1 upon 6. Okay, E1 is known 1 upon 6. So here I should write 1 upon 6 plus here I can write 1 upon 5 upon 6. I should write 5 upon 6. Okay, now let us go to A given E1 and A given E2. What does that mean? A given E1 means what? Let's write it here. A given E1 means okay, he reports it to be okay. A given E1, A is he reports it to be 6. Given that E1 is actual 6. So what does this mean? This means he speaks truth. So that's the truth probability, 3 by 4. Got it?
Yes, sir.
Okay, so that's 3 by 4. And what will be A given E2 then? He reports 6, but actually it is not 6. So that is a lie probability. That's 1 by 4. So A given E1 is 3 by 4. And A given E2 is 1 by 4. Now you can find it. It's 3 in the numerator. 3 in the numerator and 3 plus 5 in the denominator. 3 by 8 is the answer. Is that right?
Yes, sir. It's right.
Okay. Okay, quite already see. Now let us try to solve it the way I was talking about. Okay. Let us take the sample space. Okay, let us take the sample space and so this is the outcome 6. Okay, this is the outcome 6 and this is the rest of the outcomes. Okay, and suppose we take the horizontal partition, and suppose we say that he speaks truth and he lies. Okay, he lies. Okay, fine. Now which probability? Okay, let's first write down the numbers. Okay, preferably we take the sample size to be something which is divisible by 6, 5, 4 and 3. So let us take it as 600. Okay, let's take it as 600. Now, how many outcomes will belong to this? 100 outcomes will belong to this. Am I right? A sixth of total.
Yes, sir.
A sixth of the total. Okay. So for this part, how many outcomes will be there? 500. Correct? For this part, there will be 500 outcomes. Aishwarya, did you get till this?
Yes, sir.
Okay. Now, out of these 500 outcomes, how many times he speaks the truth? 3/4 times. Okay. So specifically, if we are talking about this, this will be 500 into 3 by 4. Okay, so how much will that be? 125 into 3, 375. Correct? Yeah, correct. That's 375. And what will be this number then? This will be 500 into 1 by 4. How much will that be? 125, 125, 125. Now, what thing do we want? Okay, see, we can also find these probabilities. Out of the 100 outcomes of equal to 6, he speaks truth 75% of the times. So this is going to be 100 into 3 by 4. That is 75, and this is going to be how much? 25. Correct? Now look, what do we want? He has reported that it is a 6. Okay? He has reported that it is a 6. And it is actually 6. Now look here. Reported a 6 can actually mean two things. It is indeed 6. Okay, it is indeed 6 and he is speaking truth. The outcome is 1, 2, 3, 4, 5, but he is lying, so that will be 125. Is it clear? You okay? Now, what is the probability that is actually 6? 75. Right? So, for he reporting a 6 means outcome is really 6 and he has told the truth, or outcome is not 6 but he has lied. And actually 6 is that. So 75 upon 200. 3 by 8. Correct? You can solve it either way you want. Now you understood?
Yes, sir.
Yes, sir.
Okay, so whichever thing you find it easier, you can go for that approach. When I was a student, I would prefer this way. Now, being a teacher, I recommend the base theorem because that is a certain way of solving the problems. Here, in case if you don't get integers, okay, let's say you take 300 or something like that, you may have got some fractions. That's fine. Okay, that's fine. If you are happy to take a larger number, just go with it. Otherwise, you can solve it using base. Okay. Okay. So probability is over. Any other doubt?
No, sir.
Okay. But you be ready with the approach, okay, which you want. In practice, you can try both approaches. Whichever approach you find convenient, you can go for it, okay? Don't spend time in deciding what approach should I take in the paper. Okay. Now let us go to probability distributions. Okay, let's go to random variables now. Okay, so this discussion will again start from sample space and random experiment and effect. Okay, specifically we will need only two things. We will need a random experiment and sample space. Okay, we will need a random experiment and we will need sample space. So we'll keep this in mind. We will keep this in mind. And first let's take an example and then I will tell you the actual definition of a random variable. How is it a function defined from the sample space of a random experiment to the set of real numbers? Okay, fine. So let's take the random experiment of tossing 3 coins. Suppose our random experiment is tossing 3 coins. Okay, tossing 3 coins. So my sample space will consist of TTT, TTH, THT and THH. Okay, TT, TH, HTHH and then HTT, HTH, HHT and HHH. Okay, this is the sample space. Let us call it S. I define okay, we define X as number of heads opted. Now when we define the number of heads obtained as a function, we immediately know that range of X. Okay, what will be range of X? 0, 1, 2 and 3. Is it clear?
Yes, sir.
Okay, now look, by going with the conventional definition of functions and the way we are used to write them, okay, TTT, okay, just give me one minute, I'm writing them one by one. TTT, TTH, THT, THH, and then the same thing with H, TT, H, TH, HHT and HHH. And suppose I go only write 0, 1, 2, 3. Of course, there are other variables as well, other values also. So suppose this is my domain and suppose this is my codomain. I know very well how to map, how to begin the mapping. Okay, X is the number of heads obtained. So this should go to 0. TTH should go to 1. THT should also go to 1. THH, where should it go? It should go to 2. HTT, where should it go? 1. HTH, where should it go? To 2. HHT, where should it go? HHH, where should it go? Is it clear?
Yes, sir.
Okay, so the thing is, it is a function whose range is a subset of the set of real numbers, but whose domain is actually the sample space. It's not always a number, right? Outcome of a random experiment is not going to be a number every time, unless you pick a number. Okay, so rolling a die, tossing a coin, picking a card, all of these are examples of well, they will give you sets which are whose elements will not be numbers. So this is a random variable. Okay, this is a random variable because it is a function. How do we define a random variable then? It is a function x defined from the sample space of a random experiment to the set of numbers. Okay, defined from sample space to the set of real numbers. So in this case, the random variable is x. Then when the outcome is TTT, the random variable's value is 0. When the outcome is any one of TTH, THT or HTT, the value of the random variable is 1. For HHH, the value of the random variable is 3. And for all other things, it is going to be 2. Okay, the value of the random variable is going to be 2. Have you understood this?
Yes, sir.
Yes, sir.
Okay, please understand this is basic. Okay, this is basic random variable. Okay, fine. See, so far nowhere we have introduced probabilities. Okay, that's what I'm saying. For sample space and random experiment, these two things are enough for defining a random variable. Okay, now we bring in probabilities. Okay, PMF, CDF of a random variable. Okay, so let x be a random variable defined from sample space of some random experiment to the set of elements. Okay, let R be the range of random variables. Okay, let R be the range of random variable x. We define what do we define? Another function. We define probability mass function PMF as a function. Okay, let me say P of x, probability mass function PMF as P of x as P of x defined from a range of the random variable to closed interval 0 to 1, such that sum of elements in the range of PMF is 1. Now let me explicitly state what this means. Let's take our example of rolling or tossing 3 coins. So the random variable has taken the value 0, 1, 2 and 3. Okay, that's range of x. Okay, so we define probability of x. Okay, P of x, we define probability of x as another function. What are we naming it? We are naming it as probability mass function. I think NCERT calls it probability distribution, that's fine. Okay, probability distribution function. And we assign numbers here. Okay, what care should we take? These numbers, whatever we write here, let's call them P0, P1, P2 and P3. Okay, these numbers which we are going to write below 0, 1, 2 and 3 respectively, these numbers should come from closed interval 0 to 1. But the only additional requirement is summation Pj as j goes from 0 to 3 should be equal to 1. Okay, that's an additional requirement. When that is there, then we get a probability mass function. Now, if the coins are fair, okay, if the coins are fair, then this probability is 1 upon it. You may be knowing that. This probability is 3 upon it. This probability is again 3 upon it, and this probability is 1 upon it if coins are fair. Right? Because if coins are fair, then each outcome is equally likely. So the probability that the random variable takes the value 2 is equal to the number of outcomes favorable to that event. Okay, well, not exactly event, but we will basically add all the individual probabilities. So 1 upon it, 1 upon it, 1 upon it. So 3 upon it. Okay, for the probability that the random variable takes the value 3, it should just be probability of triple H. That's 1 upon it, because all outcomes are equally likely. Have you understood this?
Yes, sir.
So probability mass function is clear. Now let us go to CDF. Okay, CDF is basically cumulative distribution function. We define CDF, cumulative distribution function. Okay, cumulative distribution function, symbol capital F of x, as capital F of x equal to probability that x is less than or equal to a particular value. Okay, so sorry, my mobile just fell down. Okay, so if I want to find the cumulative distribution function here is less than or equal to that, so we start with the smallest. Okay, nothing to be written here. Okay, so P naught. What is the cumulative distribution function's value at 1? Addition of all the probabilities to that. For 2, P naught plus P1 plus P2, and for 3 it has to be 1. Right? For cumulative distribution function, the final value should always be 1, because addition of all the remaining probabilities, including the last one, should be 1. That's the requirement for a valid PMF. Did you get what CDF is? It's cumulative probability. Okay,
Yes.
it is cumulative probability. Okay, very good. Okay, see, cumulative means two or less than 2. Okay, that's cumulative. So all previous values of the random variable smaller than that, and the given random variable value, it's 2. So for cumulative at 2, we should be adding all probabilities till 2. So P of 0 plus P of 1 plus P of 2. Got it?
Sorry, sir.
Okay. Now there is one aspect of cumulative distribution function which you may not have noticed, and that aspect is it is always increasing. CDF is always increasing. Okay, because, well, of course we never write the probabilities of impossible events, so these probabilities will always form a positive sequence, right? A sequence of positive numbers. Now individual probabilities may increase and decrease, right? But f of x is always going to increase, because every time we are going to add a positive number. So CDF is always increasing, and 1 always belongs to range of CDF. Okay, 1 always belongs to range of CDF. Rather, 1 is the maximum value in the range of CDF, because, well, eventually it will become 1 at some stage. Clear? Yes?
Yes.
Okay, fine. Well, you don't have the continuous variants, right? You don't have continuous random variables. You only have discrete random variables. Okay? I checked again, but I did not find any mention of continuous random variables anywhere. So I'm not taking that. Yeah, see, NCERT just calls it probability distribution, but the type of random variables that we are discussing, discrete random variables, we call it probability mass function. Okay, but okay, let me write it here. PMF is probability distribution. PMF is probability distribution in C here. Okay. Okay. One last time I'm going to tell you the expected value. What is the definition of expected value of a random variable? Summation pi xi. Okay, summation pi xi. Now let us find out the expected value for this. Okay, so what we are supposed to do is we would like to multiply every value of the random variable by its corresponding probability. So it is 1 upon 8 into 0 plus 3 upon 8 into 1 plus 3 upon 8 into 2 plus 1 upon 8 into 3. Okay, right. Okay, so 8 in the denominator, 0 plus 3 plus 6 plus 3, 12, 12 by 8 or 4 by 3. Okay, 4 by, oh sorry, not 4 by 3, 3 by 2, 3 by 2, 3 by 2. Okay, expected value is 3 by 2. We can similarly define expected value of x squared, or in general x raised to n, summation pi into x I raised to n. I can also define the expected value of sin x. It will be summation pi into sin of x. Okay, remember that. They may ask you a question like this. Okay, for any function of x, expected value is defined similarly the way we define summation expected value of x. Okay, so what is the expected value of x squared? Summation pi into xi squared. So it will be 1 upon 8 into 0, 3 upon 8 into square of 1, 1, 3 upon 8 into square of 2, 4, plus 1 upon 8 into square of 3, 9. Okay, it will be 3 by 4, but let's find it out. 3 plus 12 plus 9, 20. Wait, did I miss anything? No, okay, no, this won't be 3 by 4, sorry. This will be 24, so this will be 3. Okay, yeah. Now finally we define variance. The actual formula for variance is expected value of x minus x bar squared. Okay, but if you simplify that, it boils down to expected value of x squared minus square of the expected value. Okay, look, if you don't understand what I mean by variance, okay, in this fashion, it is actually summation of pi into xi minus expected value of x squared. That's exactly how we define variance in statistics. In statistics, except for probabilities, we have frequencies divided by capital N. Okay? Fine. So in this case, can you find the variance? Yes. In this case, what will be the variance? Expected value of x squared, 3, minus square of the expected value, 3 by 2 square. Okay, now let us also find out the variance by the actual the definition. Okay, E of x bar x minus x bar squared. Okay, look here. Variance of x by definition. It's like finding the derivative using first principles. It takes a lot of time. Summation pi into x minus that. Okay, so first probability is 0. A 0's probability into 0 minus 3 by 2 square plus 3 by 8 into 1 minus 3 by 2 square plus 3 by 8 into 2 minus 3 by 2 squared plus 1 upon 8 into 3 minus 3 by 2 squared. You understood, right, what we are doing here? These are x values. The values that the random variable can take. From that, what are we subtracting? Expected value, 3 by 2, 3 by 2, 3 by 2, 3 by 2. Then we are squaring. And at the end, we are taking the We are multiplying that by the corresponding probabilities. Understood?
Sir.
This is quite often a very complicated task, but they may set the problem in a way that you are forced to use the definition of variance and not the shortcut. Okay? Variance by definition. So let's take 1 upon 8 common. 3 by 2 squared, 9 by 4. Now 1 minus 3 by 2, negative 1 upon 2. Negative 1 upon 2 squared, 1 upon 4. Let's not forget this 3, so 3 by 4. 1 upon 8 taken outside. 2 minus 3 by 2, 1 by 2 squared, 1 by 4, so again 3 by 4. 3 minus 3 by 2, 3 by 2 squared, 9 by 4. Nine plus 3, 12. So 4. So 3 by 4. Okay, so we've got the same answer by the shortcut as well as the definition. What is variance? What is standard deviation? Standard deviation is root of variance. Okay, you can find the standard deviation easily by finding the root of variance. Is it clear?
Yes, sir.
Let me again remind you for one last time that expected value definition here is actually the definition of mean in in statistics. How do you write it? We just say fi upon capital N into xi. Yes.
What does the value 3 by 2 indicate?
Okay, 3 by 2. The value 3 by 2 indicates if you do the experiment many times. Okay, if you do the experiment many times and if you take the average of all the values that you got, okay, 0, 1, 2, 3. Now obviously 1 and 2 will be more in number than 0 and 3 in general, correct? If you take the average of that, you will get 3 by 2 approximately. That's the modern definition of probability. Okay, that's why we call it expected value, but it doesn't belong to the range of the random variable. What it means is do this experiment 100, 1000, 10,000 times. Multiply every value by its corresponding frequency and divide it by the total number of frequencies. That's exactly what I said here. Got it?
Yes, sir.
Yes? Okay, that's a good question. Okay. No doubt, right, till now in probability? Take it. Okay. The last part is binomial distribution involving Bernoulli trial. Okay? Fine. So let us first discuss what do we call Bernoulli trial. Okay, Bernoulli trial refers to a random variable whose range has only two outcomes or has only two elements, fondly called success and failure. Okay, what do we call these outcomes? Success and failure. See, look, the random experiment associated with a Bernoulli trial need not have only two elements in its outcome. See, for example, suppose S is 1, 2, 3, 4, 5, 6. Now, suppose I call my Bernoulli, okay, or call, let's say I say my random variable is X, okay, and say it's a function defined from S to the set success, failure. And let me say my X is, okay, if the score is less than or equal to 2, it's a success. Okay, and if the score is greater than 2, then it's a failure. That's how I define it to be. Okay, so clearly, if I now continue this and get the success probability, What is the standard notation for success probability? Small p. It will be 2 by 6 or 1 by 3. And what is the failure probability? Okay, 4 by 6 or 2 by 3, which basically give me p plus q equal to 1. Got it? Now, those success and failure, those are totally subjective. Those depend on the corresponding or associated Bernoulli trial. In some cases, we may even consider a piece to be faulty as a success. Okay, so those are not, don't go by their usual names or usual meanings of success and failure. Okay, fine. So for a Bernoulli trial, if I want to write down the PMF, it will consist of only two things. Okay, success and failure. Success probability P, failure probability Q, P plus Q equal to 1. Okay, P plus Q equal to 1. And this is the probability of X equal to success, X equal to failure. And this is, well, it's, oh sorry, this is the value of the random variable. We may call them 0 and 1 to fit the definition of PMF. Okay. Take care. Now, what is binomial distribution? What is binomial distribution? Binomial distribution requires us to have n independent Bernoulli trials. Okay, n independent Bernoulli trials. What does it mean? It means the outcome of the previous Bernoulli trial should not affect the outcome of the next Bernoulli trial. Okay, n independent Bernoulli trials. What is the random variable here? X. X is the number of successes. Okay, the range of X immediately follows 0, 1, 2, 3, up to which number? Up to n. Because how many times are we repeating the Bernoulli trial? N times. So range of X will be 0 to n. Is that clear? Yes?
Yes, sir.
Now, what is the formula for probability that X takes a value R? Now, the reason why we use R here is we require NCR formula. NCR P raised to R Q raised to n minus R. Okay, the formula is NCR P raised to R Q raised to n minus R. Now, the reason why we call it binomial distribution is that the formula also follows from P plus Q raised to n equal to, or better written as Q plus P raised to n equal to 1. Okay, because P plus Q is 1. And now we can expand this. We can say NC0 Q raised to n P raised to 0 plus NC1 P raised to 1 Q raised to n minus 1 plus NC2 P raised to 2 Q raised to n minus 2, and so on till the last term NCn P raised to n Q raised to 0. Okay, we can write that equal to 1. Now, because all the trials are independent, okay, because all the trials are independent, we can apply this formula. If the trials are dependent, then we do not call it a binomial distribution. Okay, we do not call it a binomial distribution. Okay, so that is P raised to R into Q raised to n minus R into NCR. That's the probability of R successes in the n trials. Have you understood this, or should I explain it again?
Got it, sir.
Got it? Okay. Last two more formulae associated with binomial distribution. Mean or expected value is NP. We can prove this. Variance of x is NPQ and standard deviation of the binomially distributed random variable is root of NPQ. Okay. Now typically they write this as x is a binomially distributed random variable with parameters n and p. N represents the number of times you are performing or repeating Bernoulli trial, and p represents the success probability. P is already defined. Okay. One result I want to tell you at the end, and that result is variance of x is always less than expected value of x for binomial distribution. Do you see why? Because variance of x is expected value of x multiplied by q. And what is q? So failure probability. It is between 0 and 1. Right? So variance of x is always going to be less than the expected value of x for binomial distribution. Clear?
Yes, sir.
Okay, that is the end of random variance. So tomorrow we will solve problems on probability and statistics. Okay, MCQs. Fine. We have one lecture to be covered. Let's see when can I cover it, because on Friday may not be possible. Are you guys available on Friday?
Sir, there is the puja at home.
Okay.
I
Fine.
mean, it's in Friday, sir.
No, then we can do it on Sunday, our favorite day. Fine. But let's first complete probability tomorrow, probability distributions. If you are okay, we can take half an hour extra tomorrow itself, so that we will solve enough number of MCQs on both probability and statistics, so that on this upcoming weekend we can take two tests, one on 3D geometry vectors and one on probability distributions and statistics. Is it okay?
Yes, sir.
Tomorrow let's take a bit extra. Maybe we can aim for 20 MCQs. Who knows? We can also solve 20 MCQs within 90 minutes. It depends. But anyways, let's aim for completing the probability and statistics part tomorrow. Okay? No matter if we are required to take an extra class. Okay? Extra class as in post our regular time. Okay? Fine. So I'll stop here. See you tomorrow. Revise everything. Tomorrow we will be solving MCQs. Okay? Good night.
Thank you, sir.